Example 2. In example 2, we're asked to deduce the dimension of A, modulus of elasticity, which is also known as Young's modulus, then B, coefficients of viscosity. Right? So let's begin with modulus of elasticity. So solution, modulus of elasticity, which is also known as Young's modulus, Y, is stress upon strain. Stress upon strain. Then stress alone is force per unit area. Strain is extension over original length. So this is the formula for Young's modulus. Stress over strain. Stress is force acting in a unit area. Strain is extension produced divided by original length L. So we're going to put the dimensions of these quantities and we'll get the dimension of Young's modulus. So this will be the dimension of force. We have gotten mLT, so minus 2 for force, right? Then divided by the dimension of area, which is L squared. Then everything divided by extension over length. The dimension of extension is L, the dimension of length is L. So we have L over L here, which will give us 1. So this gives us mLT to minus 2 divided by L squared. Then here we have L over L, which is 1. So this term here is gone. Everything here, this is 1, this is 1. So we have 1 over 1. It's out. So we have this to compute. So this equals mLT minus 2 upon L squared. Remember here is to power 1. So this will give us mL power 1 minus 2 by indices. Number of the same base divide the powers are subtracted in this fashion. Then t to minus 2. This equals mL. When you do 1 minus 2, you have minus 1. Then t to minus 2. So the dimension of Young's modulus is m L power minus 1, L to power minus 1, then t to power minus 2. This gives us the dimension of Young's modulus. Now let's go to coefficients of viscosity. Coefficient of viscosity is given by tangential force per unit area all over the velocity gradient, dv dx. This gives us the coefficients of viscosity. Again, we're going to substitute to solve. So force over area, we have gotten the dimension of force as mL t to minus 2 upon this area is L squared, that's length times length, then dot 1 upon dimension of, this is dv, that's change in velocity, which will still possess the dimension of velocity, which is Lt to power minus 1 all over dx, which is length, change in length, which still possesses the dimension of length. So that will be L here. So this will give us m, number of the same base dividing here by indices. We have L power 1 minus 2, then t to minus 2 multiply, this is multiplication here. This is multiplication. Multiplied 1 over Lt minus 1 over L. This L goes with this L. And we're going to have m L to power minus 1. That's 1 minus 2. Then t to minus 2 multiplied by 1 over t to minus 1. And this gives us m L inverse t to minus 2 times t to positive 1. When this t inverse goes up, becomes positive value in the power. So we are going to apply indices again. We have t here, we have t here. So we're going to add their power since they are multiplying. So this will be L power minus 1, t to minus 2 plus 1. This gives us m L minus 1, then t to minus 1. And that is the dimension of coefficients of viscosity. So this is for this. In example 3, we are asked to show that the following relation for the time period of a body executing simple harmonic motion is correct. We are given this equation to show that it is correct. So we go back to our dimension. Solution. T is given to us as 2 pi square root of L over G. Now, this is the right hand side. This is the left hand side. Now, T is period and it's going to be in seconds. This we don't know. Let's work with the right hand side to prove the left hand side. So we're going to work with this to show that it should possess the dimension of T. So let's start working with this. So this is the right hand side. This is the left hand side. So we're going to use the right hand side to prove the left hand side. So we have 2 pi square root of L over G. Now 2 pi here has no dimension at all. So we're going to proceed with square root of L over G. Now L is length, which still possess the dimension of length, which is L, capital L. G is acceleration, which we have gotten as LT to minus 2. Alright? Now, what we have here is L over LT to minus 2. So when we have L over LT to minus 2, this L here can cancel this L. So we have square root of 1 over T to minus 2. And that gives us square root of T to positive 2. When you have T to negative 2 here in the denominator, you can bring it up to become T to positive 2 in the numerator. Now, if you have square root of T squared, obviously that gives you T. So this is the right hand side and it is now equal to the left hand side. So the equation is dimensionally correct. This is the left hand side and we pick this as the right hand side and we have gotten that which is also in the left hand side. This implies that the left hand side equals the right hand side. So the equation is dimensionally correct.